so I will be talking about the design of carbon-based materials based on carbon heptagons, sp2 hybridized carbons. And we constructed several models that can be used, and hopefully in the future sometime maybe they can be synthesized. Before I start, I just have to give some analogy with the 1D topology. We can talk about like straight line that is not curved, it has zero curvature, or like a circle where it's like a small circle has a large curvature and a larger circle has a smaller curvature. And of course the curvature can change in a sine graph, but we will apply this to surfaces. And here's this pattern for the graphene. And you can see hexagons that made the graphene, and you see the shaded hexagon and not shaded. So the number of hexagons that are actually required to make graphene, to synthesize it from molecules, from benzene rings, is actually smaller. It's 3 times smaller, because when you combine them, you can see that the shaded graphenes created a space. It's a hexagonal space between them. And so in topology, this pattern is called Schläfli symbol truncated 3-6 pattern. And so that's the pattern we will be using for the constructions of all materials, but we will replace hexagons with pentagons and with heptagons, and we will see what happens. This is the graphene layer that is curving, and when it's curving in one direction, it creates the nanotube. And nanotube has curvature in one direction but not in the other one. Well, we could replace hexagons with pentagons, and what it does is that it creates a curvature. That material would have to curve because there is a shortage of the vertices there. And you can see that it actually forms known structure, the C60 fullerene. So the heptagons are the pentagons create a hexagonal space between them, and that's what makes it curving. There are 12 pentagons in that structure, and that number is actually calculated. It has to be 12. I'm not going to go into details. But when we replace pentagons with heptagon structure, it's called a hyperbolic soccer ball. And there's a negative Gaussian curvature in that structure, because in one direction it curves like outside of our view, and then in the other direction it curves toward us. So the curvature happens in 2 opposite directions, and that's what by definition is a negative curvature, Gaussian negative curvature. And that pattern is called T37, truncated 37 pattern. But this structure, when it goes continuously, it will run out of space. And if we add layer by layer, extra layer of heptagons around the central one that is shown in red, when they start growing, you will see that this is going to curve more and more. Actually, I should wait till this one shows the second layer. So we will be adding the heptagons to this. And when it starts growing, the 2 edges of that surface at some point may come closer to each other, and they would start cyclization. So it would close and make a cycle there. You can see that right now, and there is this cycle that is formed. This is the computer modeling of the growth in hypothetical like polymerization of heptagons in a 2 + 2 + 2 fashion. There are more layers added around the central one, and there are more cyclizations happening. With that growth, it can make just about anything. When we do this randomly and doing the simple molecular mechanics minimizations, we got this structure, just one of the random structures that is created. But we were wondering if this can be directed, and so the triply periodic minimal surfaces can be made. And so this is, there are three examples that I've shown there. The first one is gyroid that was just recently discovered in 1990 or in that time by Alan Schoen. And the two others are Schwartz P and D surfaces, chosen because they're convenient for that modeling. They were known since like 19th century. And so the gyroid has that interesting symmetry. It doesn't have planes of symmetry, but there is certain symmetry there, and it's, at some point it's a hexagonal symmetry. So fitting heptagons there is not quite easy. And so those units, they can combine and form material with interconnected channels that go at a certain angle to each other. The work on gyroid materials has been started quite a while ago, but the old designs contained flakes of graphene and not the atomic scale. And there's another surface, it's called P-surface, that is a chamber with 6 openings, and they can combine with each other through those openings and make a larger size structure, 3-dimensional, with also interconnected channels at 90 degrees to each other. There are 3 axes there, and so this is a highly symmetrical surface with cubic symmetry. There is another D surface that has symmetry that is tetragonal. There is like a comparison to the carbon in diamond, and so that's why it's called D surface, with tetrahedral arrangement of those openings, and they can also combine with each other and form 3D structure. So this is the one surface that has been actually modeled in 1992. That's the first example that has only T37 tessellation and nothing else. There are a lot of examples in literature where this TPMS surfaces are constructed out of octagons and in a different combination of heptagons with octagons and hexagons, but this is the only one so far surface that has been known that has pure T37 tessellation. Why is that important? Because if we constructed this just out of the heptagons, due to the symmetry, we don't want to mix it with anything else. It would be really hard to do that on a random basis. And so that's why it's important to keep this just T37 tessellation. That's what we were after. And we constructed, okay, so this is the 4D units that combine and make this material highly symmetrical. The density we calculated is 129 grams per cubic centimeter. And we designed our own D surface, but of course, that not a pure T37 tessellation. We added this atoms shown in red to preserve this hexagonal symmetry required for the cubic symmetry. So this is cubic face-centered material. It actually has a higher symmetry than the one that was known. And we also try to construct the P-surface, and that is really hard to do. So this one is actually has one hexagon replacing the heptagons, and that also creates the cubic symmetry. We can see this in the 3D space, and it has 2 equal sides. One of the sides, I will talk about this later. But when we place the hexagon, you can see that it's much easier to do those highly symmetrical surfaces, because hexagon has that symmetry that fits nicely, perfectly in the cubic symmetry with the C3 rotation axis. The density of this one is 108 grams per cubic centimeter. And when it's combined in the 3D structure, it's this one that is prepared. Now I want to talk about the 2 different surfaces, why they could be unequal. Here's an example of Euclid space with 2 surfaces that are not equal. You can see that each fits nicely over the ridges, and those 2 surfaces can be parallel. Okay, well, we constructed the P-surface that is pure T37 tessellation. So that was a big discovery. My student did this over the summer. We have a summer research at our college funds, and he spent the whole summer, and he discovered this. It is remarkable how this T37 could fit into the cubic symmetry. But the two surfaces are not equal. And whenever you construct that whole material, you see that's actually tetragonal symmetry. One axis is longer than the other two. And that creates this material with interconnected channels. And we created another one that is also two unequal surfaces. And what we tried to do is create two parallel surfaces. In 2D space, it's easy. You've seen those examples, the egg boxes. But in 3D space, it's just kind of really hard to imagine. How would you do them parallel to each other? And so here's what we constructed. The yellow is a copy of the blue one. And we put it inside itself. You see that the yellow fits inside the blue one. The small chambers goes into the large chambers and vice versa for both surfaces. We calculated the density is 227, much larger than the previous two. And here's this three-dimensional space of that material. And we've calculated the density of states. These materials range from good conductors to semiconductors and to actually like almost like an insulator. And so there's a lot of work to do, but we've discovered 5 new models and 1D surface, 4 P surfaces, including the double layered one. And one model we're proud of is that it's just using pure T37 tessellation in addition to the one that has been known. And both of those, they have 12 heptagons according to what is required. So I used all of my time. Thank you. And if you have any questions, I can try to answer.
Thank you for the presentation. Maybe one quick question from the audience. You can either type it in the chat or ask it directly. Maybe very briefly, could you comment briefly on the experimental side? So how much control is there in synthesizing structures like those that you have presented about?
Right, this is all computational modeling, and we did the molecular mechanics, and you can see that they're randomly forming whatever. And so in a real synthesis, it would be hard, it would be a big challenge. It would not be even like maybe possible to do them in a high symmetry. But there are other methods like top-up synthesis from bottom to top, and that is using pre-assembled symmetrical units. That would be the way to do it.
Right, thank you. Fascinating. All right, let's thank the speaker again for the nice talk. Thank you.